Hello, everyone, and welcome back to our annual Corrosion Forum on 2022, focusing on energy transition, corrosion, and material challenges. Our next session and third session of the day is going to be on offshore wind, and we have two wonderful presentations for you. But our next presentation and first of the two sessions would be on challenges in corrosion protection for offshore wind foundations, which will be presented by Dr. Anthony Setiedi. Now, just before he starts, I'll give you a brief background into his introduction, into our speaker. So, Dr. Setiedi has a strong record of delivering technical and project management roles throughout his 20-year industry experience and academia. His work has primarily been in offshore and oil and gas industry prior to the transition to offshore wind. He is currently the chief consultant at Thistled, where he is responsible for corrosion protection design for numerous offshore wind developments in the UK, Europe, and Asia. Dr. Setiedi has a BEng and PhD from the University of Sheffield, and he's also a fellow of ICOR and a chartered engineer. His work experience over the last 20 or so years has been across Thistled as a chief consultant. He's worked at IncTech as a principal engineer, Saipem as a coating engineer, Capsys Intertech as a corrosion/project engineer, AMEC Nuclear as a materials engineer, and also the University of Sheffield as a corrosion researcher. So with that, I'd like to introduce him and thank him very much for his presentation today. On to yourself.
Thank you, Ollie, for the introduction. Thank you, the ICOR Aberdeen, for having me to present this today. The title of my talk is about challenges in corrosion protection of offshore wind foundation. Just to give you a slide pack of what I'm going to be speaking about today. I think Thistled is quite a new company, especially in the eyes of the majority of the oil and gas people who are potentially here. So I just want to explain who we are, and then I'm going to go into offshore wind structures, the corrosion zones that we consider, the current key challenges and how we approach them, future challenges, and a summary slide at the end. So who are we as Thistled? A lot of people will say that it's part of Wood Group, but we're not. Thistled is an independent company that was set up about 6 years ago by our chairman, who's Alistair Muir-Wood, and Christian Thistled, who are based in the UK and Denmark, respectively. We are focused on offshore wind, and we are more focused now on offshore wind foundations. So that's who we are. We are based all over the globe, and our experience spans from America to Asia. Obviously, majority of the projects that we do are in Europe. In terms of what we deliver engineering services. We deliver a bit of the front end, where we do a lot of geotech and met-ocean surveys. But what we're considering now as one of our focus is obviously the offshore wind foundation design, and corrosion protection design is front and center in that regard. How we're different from the other suppliers? Well, we do try to automate a lot of our work to try to streamline our deliverables and to streamline the actual steel. And one of those things is partly from corrosion design. The way we can do our corrosion design would help in terms of shaving steel costs. I'm going to go now into a little bit of background into the offshore wind structures. So an intro to offshore wind. We are in the renewable sector, which is constantly growing. This is from the 1970s all the way up till 2019 from the IEA website. And then what's surprising to me is coal is still quite big in worldwide. But as you can see, there is going to be a trend of renewables going up as fossil fuels go down. We currently have roughly 51 gigawatts installed. We expect to reach pretty much quadruple that by the year 2030, which is a big challenge. Just to give you a context, about 1 megawatt is approximately enough to power 300 homes. So what's the deal with offshore wind? Offshore wind, we have different types of foundation that we need to put the turbine on. So over here on the left-hand side, we've got the turbine on top of a monopile. in the center is a jacket structure whereby the turbines will go on here on the transition piece. And then the far right-hand side is a floating wind foundation, which is currently still in its infancy, but they are starting to go into productions as well. What affects the different structure types? I have to apologize. There's one structure type that I missed out, which is gravity-based. It's a concrete structure, but they are typically in American waters, and there are difficulties in terms of making that and getting them into the installation area. But essentially, what are the primary factors that affect the structure type is the water depth. So depending on how deep the site is, you can go with either monopile or jackets, up to roughly about 60 to 100 meters. And beyond 100 meters, you're looking into floating. It will also depend on the ground conditions. Some sites are more suited for monopiles. Some sites are more suited for jackets, primarily in terms of how hard or how soft the ground is. And therefore, that affects the penetration depth that you can do onto the soil. The third factor that is sometimes not seen is the fabrication availability, as well as the transport and installation availability as well. These things will come into play because there are sites which are more amenable to using to building jackets rather than building monopiles. Majority of monopiles factory are in Europe, and therefore a lot of the work that we have to do is Europe-based and then transported to, let's say, to America through the Atlantic. So fabrication is always a tricky one to try to include, and then because there are so very few monopile fabricators, they are generally very busy, and to get a window to slot in the work that you have to do, it can be quite tricky. In terms of the selection of the foundation structures that we have, monopiles are typically considered to be the most economical for offshore wind foundations. So monopile itself, there are different components within the monopile. If you can see on the picture on the right-hand side, the yellow bit is essentially the transition piece. The white bit at the top is the turbine tower, whereby on top of that turbine tower will sit the turbine and the blades, so the nacelles and the blades. The yellow transition piece would typically include boat landings, external working platforms, and also internal working platforms. And then the bottom area, which currently looks non-coated, is the actual primary monopile foundation, but that could be a jacket or that could be a floating structure. Nearer to the bottom, you can see some rocks there on the seabed. That's just to protect it from moving about and in case of any scour. This one is to show you what a transition piece would look like. On the left-hand side of the picture is a traditional monopile transition piece, which then gets onto the monopile as an MP and TP, sorry, monopile / transition piece bolted connection. That's the traditional way of building these monopiles. On the middle picture is a concept of a TP-less. So therefore, the monopile goes all the way to the top. There is no transition piece. The transition piece essentially is combined within the monopile body. And then what you have is attachments on the outside for boat landing. And also there will be an internal cassette that will be fabricated and installed for internal workings of the foundation. On the right-hand side of the picture, just to show you what it looks like on the inside, there are typically 2 to 3 levels internally of working platforms. The top one is a bolt tying platform whereby we connect the TP, the transition piece, to the turbine. There is a middle platform called the switchgear platform, and then this is typically where we have a lot of the electrical equipment for the workings of the turbines. The cables go up from the bottom of the sea all the way through that third platform they'll call the airtight platform, and then it's typically terminated at the switchgear platform, which is the middle platform, before it then goes up to the turbine. The bottom platform is called an airtight platform or an airtight deck. They are not completely airtight, but they are as airtight as they can be. And the idea for the airtightness is to keep the corrosivity level above the airtight deck to be a lower classification than what it is when you are exposed to the water. So now we go into a corrosion zone definition. The picture on the right-hand side came from VGB standard, which is the German standard. And then what we have to consider, especially for monopiles, is what happens on the external and what happens on the internal. There is the atmospheric zone, which is essentially above water. There is a upper splash zone and a lower splash zone, which we have to consider. And then we have what we call an immersed zone or a submerged zone, which is basically where the steel is in contact with the water. And we also have buried zone where the steel goes into the ground itself. So what's the issue? Well, structures are made of carbon steel, and as you all know, carbon steel corrodes. So what can we do to mitigate that? It's the usual corrosion protection philosophy will apply, as we already know. We typically have corrosion allowance, and then we then provide a barrier, which is coating. Also, we put in cathodic protection, especially for areas below the waterline. In some cases, we do use CRA. Stainless steel is sometimes used internally, typically in the atmospheric zone, not necessarily in the submerged zone. So in the submerged zone, primarily it's carbon steel. The codes and the standards, just to give you an outline of what we follow. Generally for offshore wind, we follow DNV RP0416. And then it delves into coating and cathodic protection, which is for coating NORSOC, and ISO 12944 is the common standard. For CP, DNV RPB401 is the standard calculation. However, there is a new standard that just came out, which is ISO 24656. This gives a bit more detail and a bit more sort of understanding on how the offshore wind structures will affect, let's say, the seawater velocity around the structures. Bearing in mind, DNV RPB401 has generally been made for offshore oil and gas and subsea components, whereby there are not that many of them on one site. For offshore wind, what we have to consider is we're looking at between 50 to 100 offshore structures, and they're all spaced roughly 1 to 2 kilometers, 1 to 2 nautical miles from each other, and those proximity can increase the seawater velocity as it goes through the monopile, and the monopiles are generally quite large. They are looking at about 10-meter diameter. So when the seawater hits that, there is an increase in the velocity around, and that affects the current density for protection. As I said at the bottom, there are other standards available. It would depend on the country and the application. So what do we have here? This is just to show you the scale. That's a monopile factory, and this is one of the monopiles that's been fabricated. You can see the size of the people there. This is 8.5 meter diameter monopile in one of the yards in Europe. So what do we need to do here? The standard design life at the moment is 25 years. However, when we go to the coating useful life, if you follow the DNV standard, we're looking at 15 to 20 years only. So what do we do next? Beyond that, we have to consider making sure that we can repair the coating. We inspect and repair in the atmospheric zone. In the splash zone, it's a bit more difficult to inspect and repair. Therefore, we have to include what we call a free corrosion SN curve, which is the fatigue curve, as well as adding corrosion allowance. So that's quite a lot of penalty, let's say for 5 years. There are life extension proposals, which goes to about 30 to 35 years, which means you have a longer free corrosion period. For the submerged zone, we can include cathodic protection in there to mitigate some of the penalty that we're going to get for the free corrosion fatigue curves. And then finally, we want to make sure that O&M is there and able to maintain the structures. So what are the key challenges that we're facing in offshore wind, especially for foundation design? At the moment, there are 5 main ones. We look at external submerge, external splash zones, external appurtenances, which is essentially sort of fixations onto the primary steel. And the other one, which is quite a big one, is the internal, especially for monopiles. And finally, how do we deal with the O&M side of things? So the key challenge one is on the external submerge. On lattice structures, such as jackets and subsea templates, if we use traditional cathodic protection using galvanic anodes, aluminium anodes, the spacing of the anodes is relatively easy because you can pretty much put them equally along the structure. Now the problem with a monopile, because of the piling forces that we have when we put the monopile into the ground, the anodes do not really survive that piling forces, and therefore we need to put the anode somewhere else which will not see the piling force, and that can only happen in the transition piece. So the installation sequence, typically the monopile is driven through, and then we will put the transition piece on top, and then the turbine will then go above that. The transition piece is where we put majority of our anodes, but because it's only at one elevation, we need to consider how is the interference factor would affect all the anodes together, because they are clumped quite closely, and also what is the attenuation that we're going to get from the anodes that are clumped together all the way down to the bottom. Now, the water depth that we're considering here is between 30 to 40 meters. So we need to consider, is the anode sitting at 0 meters? Can that actually give protection at 30 meters? So what's our approach? We typically approach by going for the deepest location and the worst conditions. We could try to optimize by having a bespoke CP design per structure, because if we look at a site with a deepest water depth of 30 meters, there can be variation in the water depth down to even 20 meters. So there is between 10 and 15 meter variation in terms of the structures that we are going to see. So we do cluster them for structural design, but for CP design, because of the fabrication process and installation process, we do try to streamline that to make sure they are essentially very similar, and therefore it's we limit the amount of mistakes that we can make. So that's the balance that we have to give when we're trying to design, and that's why for the moment we design to the deepest, and then we apply that across the board. There is potential of using ICCP. The good thing about ICCP is that it's it has that advantage of flexibility in terms of the current output, and there is potential there to attenuate further. But the problem with ICCP, it's an active system, needs power supply and control throughout lifetime. So there is positives and negatives that we have to consider. For a sacrificial anode system, and even for an ICCP, our approach has been to coat the monopile all the way down to seabed and a little bit further beyond seabed, following the NVRP 416. ISO 24656 gives you that additional velocity safety factor that you need to consider. As I mentioned before, there is limitations on placement of sacrificial anodes on the structure, so they can only be placed on the transition piece, and potentially using an anode cage, which will then get deployed after the monopile has been installed. But what we see is that because of the clustering of the anodes in one elevation, we do need CP modeling. Here is just a an example of what we did on one of our projects, whereby we clumped the anodes right at the top there, whereby this is this blue here. The section that's on green is actually where the boat landing was. There is no anode around there. And we see how that attenuates all the way down to the bottom. And what we see is that at this water depth, which is around 30 meters, we do still see protection potential of around minus 900 millivolts, which is good for mitigating against MIC as well, especially in the upper buried zone. If you don't meet that, then one of the things that we will put in is an anode cage, which we can then locate further down the monopile. However, that adds an extra complexity in terms of installation and in terms of attachment of the cabling and to make the continuous, to make the electrical continuity to the monopile. In terms of challenge 2, splash zone, especially external splash zone, is a challenge for us. And the problem with here is that CP is not effective, especially in the upper zones. Repair can be difficult, and there is obviously a driver to limit the amount of personnel and therefore HSE exposure. These structures, as I say, they only between 50 to 100 structures in the ground. So you want to try to limit the amount of time you have to go to each and every single one of them. The challenge that we face is that from a coating life point of view, the coating useful life that we could take in the design is between 15 to 20 years. And after that, we have to use a free corrosion curve and a corrosion allowance, which means we get a massive penalty cost in terms of weight. And in a typical project, we're seeing between 1 to 2%, whilst that may not sound a lot. But if you consider these are a 60, 70 meter long monopile with a diameter of 8 to 10 meters, it's quite a lot of money and it's quite a lot of weight that needs to be added. So what do we do in terms of how we deal with this? We try to use at the very least something that can have the 20 years rather than 50 years. And at the moment that in DNV, we have to use a glass flake system. There are potentially other products that we can use that can go beyond the 20 years. What we then do is we continue with using a design factor of 3, which is one of the highest one that we can put in for offshore wind structures. And that gives us a little bit of safety factor in terms of how the structure will behave. In other developments, there are products which can go up to 30 years. I think DNV just put out a note or a publication to say that there are a couple of systems that have been used up to 30 years in the splash zone, and they came back with the industry knowledge that's still standing. However, there are no standards yet to effectively correlate, if a coating supplier wants to extend that lifetime, other than having the track record of the structure being underground for 30 years. The other challenge that we always face is the external fixations. So these are the boat landings, the external working platforms, the attachment with fasteners, so bolting, and sometimes there is quite a bit of material mismatch, which could raise the galvanic corrosion issue. So how do we deal with that? We typically go for an additional corrosion allowance to put that in, especially for these areas which is critical for people to access. We increase the coating thickness again to try to mitigate against early failures, because it's quite difficult to go out there and try to repair all of these, especially at the upper splash zone and lower splash zone. For the galvanic issue, that there are some in the external working platform as well as internal, whereby there are mismatches. For example, nowadays people want to use aluminium railings, but obviously aluminium and steel are in different ends of the galvanic spectrum, sorry, electrochemical series, and therefore you need an isolation to make sure that you don't essentially corrode well, sacrifice the aluminium, for example. What we need to do as well is to make sure that the material selection is based on the local conditions. For example, the tropics will be at a higher atmospheric corrosion compared to the North Sea. Challenge 4 is probably one of the more challenging things that I've seen in offshore wind. Previously, for offshore wind internal of monopile, the approach for DNV is to say for flooded members we can use oxygen deprivation. Due to the size of these monopiles and the size of water that's in there, and then there's always potential of breach of oxygen and also seawater, because we do have cable entry zones whereby the cables from the outside needs to go on the inside of the monopile. It's not considered that it's oxygen free, and therefore there is always replenishment of oxygen and water inside, which means corrosion occurs, and we've seen that in the past. And the approach then was to retrofit anodes inside. The first anodes that were put on were aluminium anodes, but the issue then was that due to the reactions that occur inside, hydrogen gas is formed at the steel interface, and due to the reaction with the seawater chemistry, they were observing some H2S, which obviously is not something that we want inside of the monopile, especially for the people who need to go into the internal working platforms. So currently, the industry is looking at providing both coating and authority protection, sometimes both, sometimes one of them. But here we're looking at coating and using galvanic anodes. In this case, we use zinc because the amount of hydrogen is a bit less. And as per DNV RP 416, we are looking at that without any water replenishment holes, because then the amount of hydrogen that zinc produces in the reaction does not currently affect the pH internally of the water. Whereby if we use aluminium anodes and ICCP anodes, we do require water replenishment holes as well as ventilation to avoid buildup of gas, as well as to buffer the pH inside. For internal of the monopile, the other approach that we have to consider is the 3D modeling, to ensure that we do have protection all the way throughout. Getting electrical continuity can be a bit more difficult to do, but it is something that we have done, and it can be employed. The other main challenge, or let's say this is one of them, there's another one after this, but the other main challenge that we have is the seabed level variation across all the positions, including the scour protection thicknesses. For external, it's relatively easy to say that, look, we're gonna deploy the anodes from one position, and it will go all the way down to the bottom. On the inside, if we use zinc, the attenuation doesn't go as far, and therefore for internal, typically we use an anode string, and the anode string, and then you can have a let's say an equidistant anode spacing. But obviously, to do that, you need to make sure that the bottom anode and the top anode are bound by the upper level and the lower level. In this case, the lower level is the seabed level. The seabed level can go between, let's say, 30 meters up to 20 meters, which means there's a 10-meter variation. So when you put the anodes down, you cannot just put a 20-meter string, because then how would that protect a 30-meter? It doesn't. So what we try to do is to go 1 meter above the seabed level, and that's the bottom anode, where it can then help to protect the uppermost buried zone as well as the bottom of the water. But because of that, across 50 to 100 locations, the seabed varies. We have to adjust our string, and we have to look at how the CP model correlates between the deeper cluster and the shallower clusters. So that's what we have here. Our approach is to have bespoke individual string or to cluster, and especially for galvanic anodes, the anodes are heavy, so installation trial will need to be conducted to make sure that they can actually be deployed safely. Another approach to this, or another problem that we're seeing, because zinc anodes are less effective than aluminium, the tonnage is very high. On the airtight platform, the space is very much limited, so we do have to share space with the cable, IAC cable coming in, sorry, the interarray cable coming in, and also for the volt lightning. And as you can see on the right-hand side, there's a picture of how the cable from the outside is going in and what the route is. So we have to consider a deployment position where it doesn't impact onto those cable entry zones. Another way that we're trying to alleviate against that is to potentially use ICCP, which is much lighter and more flexible in terms of deployment. As I say, the downside is we do need power, and that's something that we need to consider in terms of how to manage, especially if there is any downtime in the power supply. But essentially, a lot of the issues that we're seeing is very much multidiscipline. We don't see it just from a corrosion point of view. We have to see it from a secondary steel design, cable routing, met-ocean conditions, the geotechnical design. So I think it's a point that I want to bring across, that CP system selection is very much a multidisciplinary issue. The final challenge that I just want to put out is an O&M. There's a lot of wind turbines. We can't expect every single one of them. So therefore, we have to go for representative locations. How do we deal with that representative positions? We look at if we can do that in a automatic monitoring. So it's one of the ways that we're doing is to install sensors into representative structures. But as well, we're looking into using a personnel to go out there as well at the same time, and to confirm that what we're seeing is actually what they are seeing as well. So in DNV, it's 1 to 20 structures. We typically require a bit more than that. We're looking at about between 15 to 25% of the structures to give us a better understanding of the automatic monitoring, as well as the correlation to the actual site data. Now, previously, the structural monitoring system are on structural responses, such as strain gauges and accelerometers, but we have started to put in corrosion monitoring sensors in our design as well. This would be very good in supporting any potential life extension of the work, and for us to better understand what's going on in real life. So that's pretty much the main challenges. There are future challenges. Current operation is looking at 25 years, but we are starting to see 35 years, and even now 50 to 60 years have been raised by our potential clients. So we need to look at how we can do that better, how we can protect it better, whether we do it from the initial stage or whether we need to consider putting in potential retrofit about halfway through the design life. There are new design challenges as well, because nowadays they are looking into removing the boat landing, and therefore for a TP-less structure, if you remove the boat landing, it's very difficult to try and figure out how or where you're going to place your anodes. So we are looking into where we can deploy them and how that would protect the structure. Impact to environment and sustainability is a major thing for us. I mean, we are in a green industry, but we are still using carbon-intensive materials. So how can we help with that? That's one of the things that we're looking at, whether we can use greener construction materials, either via manufacturing routes or otherwise. And the other future challenge there is decommissioning. How do we deal with that? And that's something that it's fairly limited. There is one site that has been decommissioned in Denmark, and we're looking on learnings from that and see what we can do. So how do you meet these challenges? I think removal of some of the conservatism in the design, but we have to be careful with that. Longer durability coating system will definitely be required. And as I mentioned before, is there a potential retrofit strategy that we can use and potentially the use of ICCP systems in certain situations? So to summarize, I've been talking about primarily monopile corrosion protection for the offshore wind industry. Current coating systems are typically 25 years to 30 years, but there is a challenge there to go up to 50 years or even higher. The CP systems are either sacrificial or ICCP. There are other ways of doing that depending on the site, whereby sometimes there is no CP system and you rely on the coating. Finally, for me, corrosion protection is a multidisciplinary issue. It affects everybody, and we have to work together with the interfaces to make sure that we get a good approach. Advantage and disadvantage of systems should be scrutinized, of course. That's normal in every case. And also the main thing that I was put in there as well, environmental impact on what we do here and whether we can make sure it's sustainable. So that's it from me, and I'll pass it back to Ollie. Thank you very much for listening. Just final thank you slide. Thank you to Reserve, who's the event sponsor, ICOR Aberdeen, and to everyone for listening. Cheers.
Thank you very much, Anthony, for a very insightful and excellent presentation. And thank you also for your appreciation to the Institute of Corrosion and to Pressive. We will now open up the floor to our online viewers and to the people in the audience for our Q&A session. So if anyone has any questions, please feel free to ask now.